I just meant oriented towards the board. Okay, guys, let's begin. So, we're well done on your tests for Chapter 7. So I've marked them and we'll pass them back to you once everybody's done. We're stopping statistics for a bit, so you notice we still haven't done Chapter 8 and 9. That's going to be our last unit, okay? We do that in Term 3. What we do for the next two tests is Chapter 4 and Chapter 5. A bit like calculus, we do skills of integration in Chapter 4 and then applications of integration in Chapter 5. And they're both very short units, so we get them both done before the end of term, and then that's going to allow us to start on our folio task and moving into Chapter 6 and 7. Now, Chapter 4, if you have a look at what I've written here, I've just said the textbook, I think, does a bad job of ordering the unit. So we're going to be doing 4A.1, 4A.2, and then we're going to jump ahead to 4D. So we'll start with A1, A2 today, and we won't talk so much about what integration is, but rather we're just going to do some area under the curve calculations. This is the skill that it leads into. So, consider the function y equals 2x plus 1. Alright, what type of equation is it? A line. Okay, so the equation of a line, y equals mx plus c, and we're asked to sketch this equation from x is 0 to x is 2. Alright, so here's my Cartesian plane. I'm going to say here's 1, here's 2. Now, this equation has a y-intercept of 1. Okay, so that means this is the first point. Alright, when x is 0, y is 1. And it has a slope of 2, which means it goes across 1 up 2. Alright, so that the coordinates there would be x is 1, y is 3. And then it goes across 1 up 2. So that would be x is 2, y is 5. And so equation of a line, there it is, we've sketched it. We can get that from our graph in our calculator, we can do it manually. We understand how to graph the equation of a line. So that's the first part. Okay, part B is find an approximate area using 2 upper and 2 lower rectangles. So we're going to start with the lower rectangles, okay? So what we're doing is we're dividing the area under this function into 2 rectangles that provide an indication of roughly how much area there is under the curve. Alright, so what I'll do, I'll draw a couple of things. Alright, firstly, here's the function approximately, right? And if we want to know the area under the curve from x is 0 to x is 2, we're trying to find this area, right? And because it's a straight line, it's fairly easy to do making a geometric argument, but we're going to start by using rectangles because they lead into some more complex functions. So I'm going to draw 2 lower rectangles, all right? So I'm going to draw a rectangle here, and I'm going to draw a rectangle here. And the area of these 2 rectangles, all right, is going to be an approximation of this area, although it's not going to equal it. So who can tell me, is the area of these 2 rectangles going to be less than or greater than this area here? Less than. I mean, look at all that wasted space that we haven't accounted for, right? It's going to be less than. So this is what we call a lower estimate, because it's lower than the actual area. And so let's go ahead and calculate that. So for the lower estimate, okay, what we're going to do, we have the first rectangle has an area of 1 times 1. And the second rectangle has an area of 1 times by 3. Okay, the height of that is 3. So we have 1 plus 3, 4, and then units squared. Alright, so the area is approximately 4. It's going to be larger than 4, right? So that's using the 2 lower rectangles. Let's do it now using 2 upper rectangles. So I'm going to sketch it again. 1, 2. And I'll show you how we draw upper rectangles. Rather than starting at the point below the curve, we start at points above the curve. So that's going to be our first rectangle, and this is going to be our second rectangle. Alright? And now this upper estimate, just like it's title insinuates is going to be larger than the total area. It's above the total area, right? So if we do the upper, all right, this one has an area of 1 times 3, and this one is 1 times 5. So we have a lower estimate and we have an upper estimate. And so that means the area is somewhere between 4 and 8, isn't it? The actual area is somewhere between 4 and 8. Now lower estimate's 4, and we can see that's obviously less than, and our upper estimate's 8, and we can see that's obviously larger than. Okay, part D, A, B, D. What will happen to the interval if you increase the amount of rectangles used? All right, so here we've used 2 rectangles. We could use 10, we could use 5. Let's have a look and see. If I was to use, let's just double it and say four upper rectangles, or 4 lower rectangles. So here's 1, here's 2. We would have that one, we would have that one, we would have that one, and we would have that one. Okay. Then we can see something. What's happening to the error here? The error compared to, look at this lower calculation and this lower calculation. Which one has more error?
The one with 2. The one with 2 rectangles.
Correct. Yeah, the one with 2 rectangles. Yes, you're absolutely right. And look, if I was to colour in this square here, all right, you can see that is the error in the first rectangle. And look how much error we've removed by increasing the amount of rectangles, right? If we increase the amount of rectangles, it will lessen our error. It's going to make the margin of error smaller in the estimate. Okay, part E. Check your conjecture by investigating the error using 4 upper and 4 lower rectangles. So if we go here, so our conjecture is the margin of error is going to be smaller, right? So here I've got 0, 0.5, 1, 1.5. All right, I've divided that interval between 0 and 2 into 4 equal partitions. So we're going to have to, let's go through first as well and plot the coordinates of each point. So we know here, this is x is 0, y is 1. I might just list the y coordinates at the top, okay? Y is 1. And what's the equation? 2x plus 1. So if we have 2 times half plus 1, that's going to be 2. 2 times 1 plus 1, 3. 2 times 1.5 is 3 plus 1, 4. 2 times 2 is 4 plus 1, 5. So we've got the y values here, and that's going to help us calculate the lower and the upper estimate. All right, I might rub out this part here. And this was 2 rectangles. That was our estimate. Let's see what it is using 4 rectangles. So for our lower, it's going to be 0.5 times 1. That's for the first rectangle. Plus 0.5 times 2. Plus 0.5 times 3. Plus 0.5 times 4. Now, let's point out one thing that's quite obvious here is 0.5 is the width of the rectangles, right? And that is common to every calculation. So when you're doing this, you don't need to put all of that in your calculator, you can just factorise the 0.5. It's the width of the rectangle, we can pull that out the front, and then it's just the sum of the heights of the rectangle, right? This expression is equal to this one, so it's a faster way to write it, it's a faster way to calculate it. And so what have we got? 3, 6, 10, half of 10 is 5. Okay? So our lower estimate has increased in accuracy. Alright, it's getting closer to the actual result because we have less error. Okay, for our upper estimate. Alright, the width is the same, so we'll factorise the 0.5 straight away. And for our upper estimate, we're drawing the triangles from the top, the rectangle, sorry, from the top end, aren't we? So we're going there, there, and there. And if you look at the difference between this calculation here and this one here, I mean, we've dropped the lowest y value on the left and we've added the highest y value on the right. Okay, that's the difference, isn't it? Okay, let's evaluate that. 5, 10, 14, half of 14 is 7. Alright, so we saw when we had 2 rectangles, the area was between 4 and 8. When we had 4 rectangles, the area was between 5 and 7. Alright, so we're narrowing down that error for the area. Part F, find the actual area, find a solution using a geometric argument. So whenever it asks for a geometric argument, that just means using things you know about rectangles and triangles and circles. Sometimes we have equations of circles. What is this actual area? Alright. And so what we'll do is we'll just say, well, that's a rectangle, we can calculate the area of that rectangle. That's a triangle, we can calculate the area of that triangle and add them together. Okay? So we look at, it's a composite shape, right? So the area of A is 2 times 1. The area of B, a triangle, is always half the base times the height. So it's half of 2 times the height is 4. It goes from 1 to 5 as a height of 4. So that's half of 8, that's 4. 6. Now it just so happens that the actual area, okay, so notice how we have these lower estimates and upper estimates, lower estimate, upper estimate. The actual area is exactly halfway between those 2 estimates. Now this will only occur for a straight line function. Okay, for curves that will not be the case. One will be closer or further away. Alright, very good. Let's move on to the next example. Alright, we have a curve here. Y equals x squared. Right. Find the integral from 0 to 2 of x squared. Okay, what this means is find the area under this function from x is 0 to x is 2. Alright, so if we're going to sketch the function x squared, we're going to sketch it from x is 0 to x is 2. And we're going to do an upper estimate and a lower estimate. We'll do the upper estimate first. And it says using 2 rectangles, right? So here's the number 1. What's the corresponding y value? Remember, y equals x squared. So 1 squared is going to be 1. That would be our upper rectangle. And then here, push it that way a bit. Here, we'll go 2 squared is 4. Alright, so for our upper estimate, we're going to have 1 times 1 plus 1 times 4. 1 plus 4, 5. Okay, so that's the upper estimate. Now let's do the lower, okay? And let's consider this curve. Alright, 1, 2. If I'm going to draw a lower rectangle, it has a height of 0. Alright, I'm taking that point furthest to the left, and that's the height of my rectangle. So the first rectangle has a height of 0. and the second rectangle has a height of 1. So for the lower estimate, we have 1 times 0, that's the first rectangle. And for the second estimate, 1 times 1, we've got area of 1. Okay, let's answer this part now. Which estimate is going to be closer? The upper. Yeah? Does anyone disagree? How come you say the upper?
Because the lower, I don't know.
Yeah, no, you're correct. By the way, you're correct. The upper estimate is more accurate.
Because we've got lots of space that we're not using.
Perfect. That's exactly it. Look at all that wasted space that's not accounted for. So if you think, like in terms of the upper estimate, all right, and compared to the lower estimate, look at all this error that's not accounted for, all right, as opposed to the upper estimate. This is how much it's overestimated by, right? That's how much it's overestimated by. Cool. So that's pretty well it. Is there anything else? State an interval for the area. The area is between 1 and 5. All right, in a moment I'm going to bring up some software that's going to help you with exercise 4A.2. But what you're doing in 4A.1 is these calculations. Now, the underestimate is actually closer. I'm looking at something now, it's actually closer. Max, you got some input?
I don't like that.
That it's closer?
No, because on mine, the way I do the way, because that's when the lower one looks closer.
The lower one looks closer.
Like the way I draw it is going to
and this is something like in the past I've sort of addressed a bit later on, but let's talk about it now because I've brought it up. Let's look at what's going on with this function y equals x squared, right? Y equals x squared, and it's concave up, which means I'm going to exaggerate the curve. It's curving like that. So let me ask you, is this closer to a lower rectangle or to an upper rectangle?
Lower.
It's closer to the lower estimate, and so because the curve is closer to the lower estimate is going to be more accurate. All right, and so this is a case that's going to crop up again and again and again. When a function is concave up, all right, it's going to have this property. The lower estimate is going to be more accurate. If a function is concave down, if it's opening downwards, I'm just going to hyper exaggerate the curve there. You can see the upper estimate will be more accurate. So I thought you guys were right as well, but then I was just considering the concavity of it. So I just wanted to correct that. This is the type of thing that will pop up, and we'll make sure we're prepared for it. Okay, concave up means lower estimate's more accurate. Concave down, upper estimate's more accurate. All right, so what you do? Try some of these out. They'll start pretty basic, although they do get a bit more complex as you proceed through 4A.